The Great Pyramid of Giza stands with a precision that mocks our modern tools. How did ancient engineers align massive stone structures without metal tools, achieving near-perfect fits across thousands of miles and centuries? This is one of history's most captivating puzzles, and by the end of this exploration, you will possess a new framework for seeing every ancient monument as a deliberate masterpiece of intelligence. We will uncover how civilizations used the stars as a blueprint and water as a level, turning impossible tasks into enduring stone. What common thread of human ingenuity connects a pyramid's corner to an Inca wall's seamless joint? How can a simple rope and a bucket of water guide a project for generations? The answers lie not in lost magic, but in a forgotten science of observation. What does it truly mean to build something meant to last forever? That precision is not an isolated wonder. From the windswept Salisbury Plain to the high Andes, ancient builders achieved what seems architecturally impossible. We find Stonehenge, where massive sarsen stones were shaped, transported, and erected into a circle aligned with the solstice sun. Across the ocean, the fortress of Sacsayhuamán in Peru displays walls built from stones so enormous, so intricately cut and fitted without mortar, that a razor blade cannot slip between them. These are not random piles of rock. They represent a global phenomenon of megalithic construction, a word that simply means large stone, but implies a breathtaking mastery over the most stubborn material on Earth. To understand their genius, we must first define what alignment truly meant to them. It was a concept with three layers. The first is celestial alignment, the careful orientation of a structure to the sun, moon, or stars, turning architecture into a permanent calendar. The second is geometric precision, the ability to create perfect squares, level foundations, and straight lines over vast distances using only simple tools. The third, and perhaps most visually stunning, is the seamless joining of stone to stone, creating monolithic puzzles that have withstood earthquakes for centuries. This is the triple challenge they faced and conquered. Here lies the core paradox that fuels our mystery. The civilizations that built these wonders did not have hardened steel chisels, no laser levels, no GPS satellites, and often not even the wheel. Our modern toolkit was absent. We assume such tools are prerequisites for precision, yet the evidence carved in granite and limestone argues otherwise. This forces a profound question. Were these achievements flukes, or do they point to a body of knowledge so fundamental, so rooted in observing the natural world, that it was discovered independently across continents? The sheer scale of the work, moving stones weighing hundreds of tons, makes the simplicity of their proposed tools seem almost laughable. Yet that contrast is the very heart of the mystery. It means the solutions were not about overpowering nature with force, but about understanding it with a deep and patient intelligence. To solve how they aligned the heavens with the earth, we must first appreciate the magnitude of the stone canvas upon which they worked. Their toolkit began not with iron, but with eyes lifted upward. For every civilization that sought to build for eternity, the sky was the first and most reliable blueprint. The sun, moon, and stars moved with a predictable rhythm that no earthly landmark could match, offering fixed points in an otherwise shifting world. This was the first principle of ancient engineering, the primacy of observation and celestial navigation. It transformed a temple from a mere building into a stone clock, a calendar, and a map of the heavens all at once. To establish a true north-south line, builders in the northern hemisphere would fix upon the pole star, the one point in the night sky that appears almost stationary as the Earth turns. By marking its rising and setting positions over many nights, they could triangulate a meridian line of astonishing accuracy. For east-west alignment, nothing was more vital than the solstices, the 2 days each year when the sun reaches its farthest northern and southern points on the horizon. By driving 2 stakes into the ground and lining them up with the sunrise on the summer solstice and the sunset on the winter solstice, a builder could trace a perfect east-west axis. This simple, patient method, repeated over seasons, gave them a foundation more precise than any magnetic compass could provide. The ancient Egyptians perfected this art with an instrument called the Merkhet. It was a deceptively simple device, just a horizontal bar with a plumb line hanging from it. A priest or astronomer would use it like a gun sight, aligning the string with a specific star as it crossed the meridian. By using 2 of these tools and sighting on different stars, they could lay out the cardinal directions on the ground with an error margin of less than a fraction of a degree. This is how the Great Pyramid's sides were aligned almost perfectly to true north, a feat that still baffles surveyors today. This celestial connection was far more than a practical trick. It was a sacred act, a way of weaving the order of the cosmos into the fabric of their world. A temple aligned to the solstice sunrise did not just mark a date, it captured a moment of divine power, allowing the sun's rays to illuminate an inner sanctum only on that special day. By patiently watching these cycles, sometimes over generations, these cultures encoded astronomical knowledge into stone, creating structures that would continue to tell time long after their builders were gone. The sky was their unchanging reference, and by learning its language, they gave their greatest works a foundation in eternity itself. With the sky providing their vertical axis, the next challenge was mastering the horizontal plane. How do you create a perfectly level foundation for a pyramid that covers 13 acres, or ensure that a temple floor stretches for hundreds of feet without a single dip or rise? The answer flows from one of the most humble and abundant resources on Earth, water. In its stillness, water always finds a level surface, a principle ancient engineers observed and turned into a monumental tool. By digging a long, shallow trench around the entire perimeter of a planned construction site and filling it with water, they created a giant, continuous spirit level. A mark made on the trench wall at the water's surface would indicate the exact same height at every point along that trench. Workers could then transfer that height mark to stone blocks or foundation posts, ensuring the entire site was perfectly flat before a single course of stone was laid. This simple yet profound use of water allowed them to establish a true horizontal datum over distances that would challenge modern laser levels. From that level plane, the art of geometry could begin. With a perfectly flat surface established, they needed to translate celestial alignments into precise shapes on the ground. This is where a simple knotted rope transformed into a master surveyor's tool. The most famous example is the use of the 3-4-5 triangle, a method that guarantees a perfect right angle. Imagine a long rope with knots evenly spaced along its length. If you take a section with 12 equal intervals and form a triangle with sides measuring 3, 4, and 5 intervals, the angle between the 3 and 4 unit sides will be exactly 90 degrees. A team could stretch this rope, drive stakes at the knots, and instantly map out a perfect corner for a pyramid's base or a temple's wall. By repeating this process and using ropes to measure consistent distances, they could lay out enormous squares, rectangles, and grids with astonishing accuracy. This was not advanced mathematics in a theoretical sense. It was applied, practical knowledge born from direct observation and experimentation. The same principles of rope and geometry allowed for the creation of vast circles like those at Stonehenge. A central stake with a long, taut cord acting as a radius became a giant compass. As a worker walked the circumference, keeping the cord tight, he could mark the ground at regular intervals, creating a perfect ring hundreds of feet across. Every curve, every right angle, every parallel line in these ancient complexes can be traced back to the intelligent application of these simple, observable principles. It was a geometry not of abstract formulas on parchment, but of physical stakes in the earth, of strained ropes singing in the wind, and of patient, repetitive verification. This demonstrates a core truth about their engineering. Complex and awe-inspiring layouts did not require incomprehensible secrets. They stemmed from a deep, patient understanding of the natural world's own rules, and the brilliant simplicity of applying those rules on a colossal scale. The real magic was in the translation, from the ripple of water in a ditch to the immutable corner of a stone destined to stand for millennia. Yet geometry alone cannot raise a wall. Once the perfect angles were marked on the ground, the monumental task of building upward began, demanding a new kind of precision, vertical truth. This is where the third principle of ancient engineering reveals its elegant simplicity, the constant dialogue between gravity and human intention. For ensuring that a wall rose perfectly perpendicular, that a column stood straight, or that a lintel was set true, the most trusted tool was also the most humble, the plumb bob. It was nothing more than a pointed weight suspended from a cord, yet in its unwavering descent, it offered an absolute reference to the center of the earth. As each massive stone was levered into place, a builder would hold the cord against its face. If the stone leaned inward or outward, the bob would swing clear, a silent but undeniable verdict. If the wall was true, the cord would brush gently against the stone from top to bottom, a whisper of confirmation. This simple act created a constant feedback loop, a real-time check that allowed for minute adjustments with wooden wedges or gravel beds before the next multi-ton block was committed. But the plumb bob's genius extended beyond checking finished work. It was crucial for transferring alignment from the planning stage to the construction itself. Imagine a complex temple layout, its key points marked by cords stretched between stakes high above the foundation trench. To transfer those exact points down to the bedrock where the stones would actually sit, a builder would simply hang a plumb line from the precise intersection of the overhead cords. Where the bob's point touched the ground, he would make his mark. In this way, the celestial alignments painstakingly observed on the horizon were translated, through a length of string and a weight, directly onto the immutable foundation. Working in concert with the plumb line was another deceptively simple wooden tool, the A-frame. Shaped like a capital letter A, it was a portable instrument of verification. If you placed it on a surface and hung a plumb bob from its apex, you could instantly see if that surface was level by whether the string aligned with a mark at the frame's center. More brilliantly, a builder could walk this tool along a prepared baseline. By ensuring the plumb line hit its mark at every step, he verified the entire length was perfectly level. Conversely, if you needed to scribe a line parallel to an existing wall, you could simply walk the A-frame along it, letting a stylus attached to one leg scratch a perfect duplicate line on the floor a fixed distance away. Think of a master builder overseeing the rising course of a pyramid's burial chamber. The air is thick with dust and effort. He watches as a team slowly lowers a granite ceiling slab into place. Before they release the ropes, he steps forward, not with a complex instrument, but with a string and a weight. He holds the cord against the slab's edge. The bob hangs motionless, a vertical thread in the dim light, touching the stone from top to bottom. A nod, the slab is true. In that quiet moment, the grand celestial plan, the geometry laid out with ropes, and the patient labor of hundreds, all converged upon the silent testimony of a dangling piece of lead. It was this marriage of the cosmic and the tactile, the eternal and the everyday, that allowed intention to become immovable stone. The true journey of a megalith did not begin at the construction site, but deep within the living earth of the quarry. Here, long before celestial alignments could be marked or geometric lines drawn, ancient engineers engaged in the first and perhaps most critical act of precision, selecting and liberating the stone itself. This was not a matter of brute force, but a sophisticated dialogue with the material, a practice rooted in profound observation and patience. The builders understood that rock was not a uniform substance. It possessed a personality, a grain, a memory of its formation. Their first task was to red the stone, to identify natural fracture lines and planes of weakness that could be coaxed into becoming clean separation points. A master quarryman would walk the cliff face, tapping with a hammerstone and listening to the tone, seeking the resonant ring of solid stone versus the dull thud of a hidden flaw. Choosing the right block from the very start was the foundation of all future precision, a decision that saved immeasurable labor and ensured structural integrity for ages. To free these multi-ton giants, they employed a brilliant understanding of thermal dynamics. One widespread technique involved building small, controlled fires directly along a desired fracture line on the bedrock. Once the stone was heated thoroughly, workers would rapidly douse the hot surface with water or sometimes vinegar. The sudden, violent contraction caused by the cooling created immense stress, cleanly splitting the stone along the prepared line. This method of fire setting allowed them to isolate enormous blocks with a level of control that pounding alone could never achieve. For finer work and to detach the block completely from the quarry floor, they turned to a more physical yet equally precise method. Using hammerstones made of a harder rock like dolerite, teams would pound a series of closely spaced holes along the base of the block. This repetitive action over days or weeks would gradually pulverize the stone along a narrow channel, effectively sawing the block free through pure, persistent abrasion. The resulting groove could then be widened with wooden wedges soaked in water to make them swell, gently prying the monolith from its ancient bed. Once liberated, the stone was not yet ready for its journey. The next act of foresight was rough shaping. Skilled workers would use their stone mauls to knock off major protrusions and begin forming the block's general profile right there in the quarry. This was a strategic masterpiece of logistics. By removing excess weight before transport, sometimes reducing a block's mass by a third or more, they dramatically simplified the Herculean task of moving it. This phase required a sculptor's eye, seeing the final form within the raw mass, and the discipline to stop before the stone became too fragile. Each blow was calculated. Each flake that fell was a step toward the future wall or column it was destined to become. In this dusty, sun-baked landscape, surrounded by the echoes of countless hammer blows, we see the essence of their practical genius. They treated each block not as an inert obstacle, but as a partner in the project. Their knowledge was tactile, earned through generations of hands-on work, teaching them how to listen to the stone, to persuade it, and to prepare it for a transformation that would outlast empires. The quarry was not just a source of material, it was the first workshop where the vision for eternal alignment was forged in sweat, fire, and an intimate conversation with the very bones of the planet. Liberated from the quarry, the stone now faced its greatest trial, the journey. To move a block weighing as much as several hundred elephants across miles of rugged terrain without the wheel or steel seems like a task from myth. Yet this was the daily reality for these builders, a monumental feat of logistics that turned coordinated human effort into a slow, relentless force of nature. The most iconic image we have is the wooden sledge, but this was no simple sled. It was a massive, purpose-built platform, likely lashed together with ropes of incredible strength, perhaps made from papyrus or other fibrous plants. The true genius, however, was not in the sledge itself, but in the road it traveled. Teams would prepare a pathway, not with pavement, but with a carefully laid surface of wooden sleepers or smoothed earth. Crucially, this track would be constantly lubricated. Evidence suggests they poured water, or possibly a slurry of clay and water, ahead of the moving sledge. This created a slick, muddy surface that dramatically reduced friction, turning a near-impossible drag into a manageable, if still Herculean, pull. For truly enormous stones, like the colossi of ancient Egypt, This operation involved hundreds of laborers pulling on great ropes in a synchronized rhythm, guided by the beat of drums or the calls of overseers. It was a symphony of human muscle and simple physics. Another widespread method involved the log roller. Here, teams would place a series of freshly cut, sturdy logs perpendicular to the direction of travel. The stone block, already on its sledge, would be levered forward onto these rollers. As the sledge moved forward, workers at the back would frantically retrieve the freed logs and run them to the front, creating a continuous, rolling road. This cyclical, exhausting process allowed a small team to move immense weights by constantly recycling a limited number of logs. It was a breathtaking display of stamina and coordination, where the rhythm of retrieval and placement was as vital as the pulling itself. But moving the stone was only half the battle. How did they ensure that after this chaotic, lurching journey, the block arrived at the temple site with its proper orientation intact? A block destined for a seamless wall had specific faces that needed to be its future top, bottom, and sides. Losing that orientation during transport would mean hours of extra work or even ruining the stone. The solution again lay in preparation and marking. Before the journey even began, master builders likely used ochre or charcoal to mark the critical reference faces on the rough stone. More importantly, they may have used a system of sighting poles. By erecting tall, aligned poles along the prepared transport route, crews pulling the sledge could keep the block on a true course. Even more cleverly, the sledge itself might have been constructed with notches or marks that aligned with these poles. As long as the pullers kept the sledge aligned with the distant markers, they could be confident the stone was traveling in the correct orientation, its reference face pointing the right way. This transformed a chaotic haul into a guided procession. Imagine the scene at a site like the Great Pyramid, a massive limestone block, its future outer face already smoothed, inches forward on its muddy track. A foreman stands on a raised platform, his eyes darting between the straining ropes and a pair of tall cedar poles planted far ahead in the desert. He shouts a correction. The teams on one side lean harder just for a moment, and the sledge's edge realigns with the distant markers. The block is not just being moved, it is being steered. This careful guidance meant that when the stone finally arrived at the foot of the rising monument, it was not a random chunk of rock. It was a pre-oriented component delivered to its approximate position with its identity preserved. The back-breaking labor of transport was in fact the first act of precise placement. The final, hair's-breadth adjustments would come later with levers and gravel beds, but those adjustments were only possible because the 1,000-person effort of the haul had been a disciplined exercise in alignment from start to finish. In this way, the journey was not an interruption of the building process, it was its vital, thunderous prelude. At the building site, the final and most intimate act of alignment began. The stone, now resting near its destined place, was still a rough giant. Its journey was over, but its true transformation into a seamless part of the wall was about to start. This brings us to the sixth principle, the keystone technique of dry stone fitting and abrasion. Without a drop of mortar to hide mistakes, each block had to be custom shaped to its neighbor with a precision that seems superhuman. The method was a slow, physical conversation between stone and stone, guided by an unerring eye and immense patience. It was called dry stone fitting, and it turned construction into a form of monumental sculpture. The process began with placement. A new block would be carefully levered and set adjacent to the one already in position. It would not fit, of course. Protrusions and high points on its surface would press against the face of its neighbor. Here, the builder used a simple but brilliant trick. He would take a piece of charcoal or red ochre and smear it over the face of the stationary stone. Then he would gently rock the new block against it. When he pulled the block away, the charcoal would have transferred onto the high spots of the new stone, creating a precise map of exactly where material needed to be removed. It was a perfect feedback system where the stones themselves communicated what was required. Now came the painstaking work of abrasion. Workers would not simply chip away at the marked areas. Instead, they used a grinding process. They would take a slurry of sand and water, or sometimes a paste of crushed quartz, and apply it to the stone's surface. Then, using a harder rock like a piece of granite or dolerite, they would rub, peck, and grind the marked high points away. This method, known as pecking and grinding, allowed for incredible control. The abrasive sand did the cutting, while the handheld stone was just a tool to apply pressure and motion. It was slow, it was tedious, but it was remarkably effective. By grinding rather than striking, they avoided creating deep fractures or weakening the stone, instead wearing it down grain by grain to achieve a perfectly flat plane. This created an iterative cycle of almost meditative repetition. Place the block, mark the high points, grind them down, wash the stone, and place it again. Each cycle brought the fit a fraction of an inch closer to perfection. Over days or even weeks for a single critical stone, the gap would disappear. The final test was the same across continents, from Peru to Egypt. A master builder would try to slip a thin blade, often made of bronze or even a stiff leaf, between the joined faces. If it passed, more work was needed. If it caught, the seam was true. The goal was a joint so tight that not even air seemed to pass through, locking the stones together by friction and geometry alone. This technique explains the breathtaking walls of Sacsayhuamán or the precision of a pyramid's burial chamber. The undulating, interlocking shapes were not random artistry. They were the direct result of this place mark and abrade method. Each stone became a unique key for a unique lock, and the wall grew not as a stack of identical blocks, but as a three-dimensional puzzle assembled one perfect connection at a time. The primary tool here was not metal or complex machinery. It was human patience elevated to an industrial scale. It was the understanding that time itself could be a resource, and that investing months in fitting a single stone was not a delay, but the very definition of building for eternity. The final alignment of the entire structure, therefore, was not imposed from a grand blueprint alone. It emerged molecule by molecule from the accumulated precision of 10,000 small, deliberate adjustments. The wall did not achieve perfection. It grew into it through the persistent whisper of stone grinding against stone. But this patient, iterative fitting raises a crucial question. How could builders working on separate parts of a vast project, or even across generations, ensure that every uniquely shaped stone would ultimately come together into a coherent whole? The answer lies in a seventh principle, one that bridges the gap between grand vision and granular execution: the use of templates and models. Before a single ceremonial stone was quarried for a temple's inner sanctum, its entire form may have first existed in miniature, carved from wood or molded in clay. This practice of prototyping represents a leap in cognitive engineering, moving construction from improvisation to intentional design. Think of a master carpenter shaping a complex joint for a fine piece of furniture. He does not start by cutting into the precious oak. First, he makes a mock-up from scrap pine, testing the angles, checking the fit, and refining his measurements. Only when the template is perfect does he transfer those lines onto the final material. Ancient engineers applied this same logic, but on a monumental scale. For a structure like the enigmatic corners of an Inca wall, where stones interlock in mind-bending polygonal puzzles, a full-size wooden template could have been the key. A craftsman would carefully construct the exact negative shape of a kneaded stone from wooden planks. This template, light and manageable, could then be carried to the quarry and placed against a raw block. Workers would simply trace the template's outline onto the stone's face, giving them a precise guide for the initial rough shaping. This method ensured that even the most bizarre, multi-angled block was performed to a specific design long before it ever met its neighbor. It turned the chaotic quarry into a precision parts factory. Beyond physical templates, there is compelling evidence for the use of complete-scale models. Archaeologists have found small, meticulously carved stone models of pyramids and temples in the regions around major construction sites. These were not mere toys or votive offerings. They were likely architectural plans in 3 dimensions. A ruling priest or head engineer could use such a model to demonstrate the final vision, to calculate approximate volumes of material needed, and to study the play of light and shadow at different times of year. More practically, for an apprentice mason, holding a detailed model in his hands would make abstract geometric principles tangible. He could see how the courses of stone stepped back, how the corridors aligned, and how the weight would be distributed. This visual and tactile planning would have been invaluable for coordinating the work of hundreds, perhaps thousands, of laborers across a decades-long project. This approach allowed for a form of ancient reverse engineering. By building small, they could identify problems while the cost of failure was negligible. A joint that proved unstable in a clay model could be rethought. An angle that looked right on a diagram but felt wrong in a 3-dimensional mock-up could be corrected. This off-site problem solving was a risk management strategy of the highest order, preventing catastrophic errors with stones that weighed more than elephants. It points to a sophisticated, multi-stage design process that blended abstract mathematics with hands-on craftsmanship. The vision began in the mind, was given form in miniature, tested and refined through models, and only then was committed to the immutable language of megaliths. This 7th principle reveals that the silence of these sites is deceptive. Before the first hammerstone struck in the quarry, before the first rope was strained on the sledge, there was likely a quiet room where small-scale models sat on a table, and the voices of planners debated angles and alignments. The true foundation of these wonders was not just in the bedrock, but in this capacity to hold the entire, finished structure in the imagination first, and then in the palm of the hand. The final stage of placement was a ballet of controlled force. With the stone now resting near its precise location, the challenge shifted from movement to micron-level adjustment. Brute strength was not just ineffective here, it was dangerous, capable of shattering months of careful work in an instant. This is where the 8th principle reveals its quiet genius, the mastery of leverage, counterweights, and the patient art of making stones walk. Primary tool for this delicate dance was the wooden lever, a simple beam of sturdy timber. Teams would insert the tapered end of such a beam under a corner of the massive block, using a flat stone as a fulcrum. Then, with coordinated effort, they would pull down on the long end. Physics did the heavy lifting, multiplying their force many times over, allowing them to lift a corner that weighed tons by just a few precious inches. That tiny gap was the window of opportunity. Swiftly, workers would slide thin packing stones, wooden shims, or a bed of gravel into the space. When the lever was released, the block would settle onto this new, slightly higher platform. By repeating this process on each corner, alternating sides in a careful rhythm, they could ratchet a monolith upward, inch by patient inch, until it reached the exact height of its neighboring stone in the wall. But vertical lifting was only half the puzzle. The final, hair's-breadth lateral adjustment, sliding the stone that last fraction into a seamless joint, required an even more clever technique. This is where the idea of walking a stone comes to life. Imagine 2 teams with long levers positioned on opposite sides of the block. One team would gently pry their side upward, just enough to tilt the stone. As it tilted, its weight would shift onto one edge. At that precise moment, the other team would insert a rounded wooden roller or a pile of smooth pebbles under the raised edge. Then, as the first lever was relaxed, the stone would settle, now slightly shifted from its original position. By rocking the stone back and forth in this coordinated way, left then right, they could literally walk it across its foundation, nudging it with imperceptible steps until it clicked perfectly into its designated slot. It was a slow, rhythmic process, a conversation between teams signaled by calls or drum beats, where patience was the ultimate power tool. For more complex maneuvers, like tilting a massive obelisk into a vertical position, they likely employed counterweight systems. One compelling theory involves the use of a large sandbox built behind the stone's base. As the obelisk was levered up from the front, sand could be slowly released from a hole in the bottom of the box. The decreasing weight on the back side would provide a smooth, controllable counterforce, preventing the stone from crashing forward. Alternatively, baskets filled with stones could be hung from ropes on the backside, their weight carefully calculated and adjusted to balance the titanic lever arm. These methods transformed an act of terrifying risk into one of measured, predictable control. The overarching lesson here is one of finesse over force. They understood that overwhelming weight could be managed not by meeting it with equal strength, but by outthinking it. A multi-ton block became a puzzle to be solved with patience and clever mechanics. The final, satisfying thud of a stone settling into its perfect place was not the sound of a struggle won by muscle, but of a complex problem solved by collective intelligence. It was the moment when celestial alignment, geometric planning, and painstaking transport all culminated in a perfect fit, achieved not with a shout, but with a whisper of wood on stone. The culmination of these techniques is etched into stone across the Andes, in the breathtaking walls of the Inca. These structures present perhaps the most visually stunning enigma of all: the polygonal ashlar walls where giant stones of wildly different shapes fit together like a colossal, irregular jigsaw puzzle. How could such a system, which seems to celebrate chaos, achieve a level of precision that has withstood centuries of earthquakes? The answer lies not in a single secret, but in the ultimate application of patient, systematic fitting on a monumental scale. The prevailing theory among researchers is a process often called the soft fit method. Imagine a master builder standing before a newly placed stone, its face now immovable. His team would take wet clay or perhaps a pliable mixture of mud and straw and press it firmly against that stone's exposed side. This would create a perfect, three-dimensional negative impression, a flexible mold capturing every bump, hollow, and angle. This mold would then be carried to the next raw block waiting in the stonemason's yard. Craftsmen would use this clay template as a guide, painstakingly pecking and grinding the new stone's face until it matched the impression. The new block was not shaped to an abstract ideal, but was custom carved to become the literal mirror image of its neighbor. When finally levered into place, the fit would be so intimate that the joint all but disappeared. Another compelling idea suggests they worked in cascading sequences. The first, lowest stone in a course would be set and leveled. The second stone would then be shaped entirely to fit against the first. Once the second was locked in, the third stone would be shaped to fit against the second, and so on. Each stone became both the template for the next and the result of the previous, creating a chain of unique dependencies. This method required immense foresight, as the shape of the 10th stone was indirectly determined by the placement of the very first. It was a living, growing algorithm in stone, where flexibility was the core principle of stability. This was not random artistry or mystical power. It was a highly systematic, yet brilliantly flexible, approach to solving two critical problems. First, it provided unparalleled seismic stability. During an earthquake, a wall of uniform rectangular blocks tends to sway as a single, rigid unit, which can cause it to collapse. A polygonal wall, however, is a network of interlocking forms. The irregular shapes lock the stones together, allowing the energy of the quake to be dissipated as the stones shift and settle minutely against each other before settling back into place. The walls were designed to dance, not to break. Second, this method allowed for the use of almost any large stone found or quarried nearby. There was no need to waste time and effort carving every block into a perfect rectangle. Instead, they could work with nature's offerings, using the soft fit process to turn irregular giants into perfect partners. The result is a wall that feels organic, as if it grew naturally from the mountain itself, yet exhibits a geometric intelligence that humbles modern engineers. In the silent, sun-warmed stones of Sacsayhuamán or Ollantaytambo, we see the final, majestic expression of all the principles we have explored. Here is celestial alignment in the terrace orientations, geometric planning in the grand layouts, patient abrasion in the smooth facets, and the ultimate triumph of custom fitting. The Inca builders understood that true alignment was not about forcing conformity, but about finding the perfect, unique relationship between one stone and the next, building resilience from 1,000 intimate connections. The Great Pyramid's sides align with the cardinal directions with an error of less than 1/15 of a single degree. This is not a lucky accident, but the signature of a civilization that turned sky watching into a precise terrestrial science. To achieve this, Egyptian engineers likely employed a method as elegant as it was patient, rooted in the geometry of a circle drawn in the sand. This proposed technique, often called the circle method, begins with a level area of desert marked with a central vertical rod, a gnomon. As the sun moves across the sky, the tip of the gnomon's shadow traces a curve on the ground. Before the equinox, when day and night are equal, a builder would mark the shadow's tip at various points throughout the day. These marks would form a shallow arc. By drawing a smooth circle that intersected all these points, they created a perfect geometric reference. The true brilliance came next. They would inscribe a square inside that circle, connecting the points where the circle met the shadow arc. The lines of that square, bisected, would point directly to true north and south, derived purely from the sun's symmetrical path on the equinox. This method required no advanced instruments, only meticulous observation over an entire day, and the geometric insight to see cardinal directions hidden within a simple curve. Yet the sun was not their only guide. For even greater precision, especially for laying out multiple pyramids across the Giza Plateau in perfect harmony, they may have used the stars. One compelling theory is the simultaneous transit method. This involves observing two specific stars that circle the celestial pole, like Mizar and Kochab in the constellation Ursa Minor. An astronomer would use two sighting instruments, perhaps simple notched palm ribs or the more advanced Merkhet with its plumb line. He would wait for the moment when one star appeared to cross an imaginary north-south meridian line directly above the other. By aligning his two sighting tools with this celestial event, he could project that perfect meridian down onto the desert floor, establishing a true north-south baseline of astonishing accuracy. This stellar method, less affected by atmospheric refraction than horizon observations, could provide the master surveyor's line that guided an entire generation of construction. The result of this painstaking work is written across the Giza Plateau. The Great Pyramid, along with its neighbors Khafre and Menkaure, are all aligned to the same cardinal grid with minor, explainable variations. This consistency tells a powerful story. It was not enough for one pharaoh's monument to be perfect. A master reference direction, a true north line, was established and then preserved, likely marked by permanent stone markers or maintained through oral and written tradition across decades, perhaps even centuries of construction. This transformed a single act of celestial observation into a sustained cultural project. The initial alignment, whether drawn in sand or sighted on stars, became a sacred datum, a piece of cosmic order fixed into the very landscape. Every architect, every chief mason for over 100 years would have begun his work by referencing that original, unimpeachable line. This case study reveals the scaling of a simple principle into a monumental legacy. It shows that their greatest challenge was not the initial discovery, but the faithful transmission of that discovery across time, ensuring that the pharaoh's house for eternity would forever face the unchanging pillars of the sky. Across the Atlantic, under the wide skies of Neolithic Britain, a different philosophy of alignment was taking shape. At Stonehenge, the goal was not a single, towering monument pointing to the heavens, but the orchestration of an entire landscape. Here, alignment was a dynamic, living process, weaving architecture, earth, and sky into a vast ceremonial observatory. The builders did not just erect stones, they sculpted sightlines, using the natural horizon as their celestial dial. The most famous of these is the alignment of the heel stone with the summer solstice sunrise. When standing at the center of the stone circle on the longest day of the year, the sun appears to rise directly over this lone, weathered sarsen, framing the dawn in a spectacle of light and shadow. But this was likely just one moment in a far more complex calendar. Researchers suggest that other stones and the surrounding Aubrey holes, a ring of pits just inside the earthwork bank, may have been used to track the more subtle 18.6-year cycle of the moon, marking its extreme northern and southern risings. This required a different kind of precision, one measured not in fractions of a degree, but in the patient observation of a moving point against a fixed horizon over generations. To achieve this, they may have used a method of terrestrial surveying that feels almost like a sacred form of wayfinding. Before a single megalith was raised, builders could have placed tall wooden posts on distant hills or existing burial mounds that were already visible on the skyline. By sighting from one post to another across miles of rolling grassland, they could establish long, straight lines that pointed to where the sun or moon would rise or set at a key moment in its cycle. These sightlines became the invisible threads that stitched the monument into the fabric of the land itself. The transport of the stones reveals a layer of meaning beyond mere logistics. The smaller blue stones, weighing up to 4 tons each, were brought from the Preseli Hills in Wales, a journey of over 150 miles. This was not the shortest or easiest route. Some researchers propose they followed paths that were already spiritually significant, what some later cultures might call ley lines, pathways believed to connect places of ancient power. By moving the stones along these perceived energetic lines, the journey itself became a ritual, a process of bringing the sacred essence of a distant mountain to the heart of their ceremonial plane. Every pull of the rope, every log placed under a sledge, was an act of alignment with a deeper, invisible geography. The final monument, then, was not an isolated ring. It was the focal point of a vast cosmological diagram drawn on the Earth. The surrounding cursus, a long, enigmatic earthwork, the nearby avenue, and even older burial mounds all seem positioned in relation to the stones and the astronomical events they mark. This integrated design suggests the builders saw no separation between the built environment and the natural world. A solstice sunrise was not just observed from Stonehenge, it was an event that unfolded along a precise axis that began at a distant horizon marker, traveled down the processional avenue, and culminated in the illumination of the central altar stone. The alignment was the experience, a journey both physical and spiritual that connected the community to the cycles of the cosmos through the very ground beneath their feet. In this misty landscape, precision was communal and cumulative, a knowledge built not by a single architect with a plumb line, but by generations of watchers who learned to read the sky's story in the silent hills. The ocean itself was their uncharted desert, a vast and trackless expanse where the horizon offered no fixed point. Yet the Polynesian navigators did not wander, they voyaged with purpose across thousands of miles of open Pacific, finding specks of land with a reliability that rivals modern instruments. Their genius offers a profound parallel to the stone masters on land, for both shared a singular secret: they learned to read a living world. Where a pyramid builder watched the stars to fix a corner, a navigator used them as a moving map. They memorized not just the rising and setting points of hundreds of stars, but how those points shifted as they sailed, creating a mental star compass that painted direction across the dome of the night sky. By day, they interpreted the ocean's subtle language, the long, deep swell patterns that refract around islands, the specific flight paths of homing birds, and the color and texture of clouds that hinted at distant land. This was not navigation by luck, but by a hyper-observant, systemic reading of natural cues, a science of wayfinding encoded entirely in memory and song. This same deeply internalized knowledge of the environment almost certainly guided their work on land. Consider the Mari, the sacred stone platforms found on islands like Raiatea. These were not randomly placed, they were precisely oriented, often aligned to significant stars or to the seasonal winds and currents that were vital for voyaging. Building a Mari was an act of anchoring cosmic and oceanic knowledge into the earth, creating a fixed point of reference in both the spiritual and the practical geography of their world. The stones were placed to mirror the order they observed in the heavens and seas, turning the platform into a stable, terrestrial counterpart to the dynamic ocean they mastered. This connection reveals a universal thread in ancient engineering. The most sophisticated tool was often not a physical object you could hold, but a living knowledge system, a cultivated intuition passed meticulously from elder to apprentice through chants, stories, and star names. A master navigator did not need a metal sextant. He carried the map in his mind, sustained by generations of accumulated observation. In the same way, the master builder of a Mari or a pyramid did not rely on a single secret blueprint. He operated from a shared cultural understanding of how the world was ordered and how stone should be placed to reflect that eternal order. The voyage and the temple were two expressions of the same profound principle. Alignment was not imposed upon the world. It was discovered within its patterns and then faithfully echoed in human creation. Whether steering a canoe by the swell against the hull or setting a cornerstone by the star's transit, success depended on a lifelong dialogue with the elements, a patient listening to the whispers of the natural world that modern tools have largely taught us to ignore. These lingering questions sometimes lead us into the realm of legend, where whispers of a forgotten science echo through time. Among the most persistent fringe theories is the idea of acoustic levitation, the notion that ancient builders used specific sound frequencies to soften granite or make massive stones weightless, guiding them into place with chants and drums. These stories are captivating, often rooted in local folklore or esoteric texts that describe a lost world where music could move mountains. They speak to a deep human desire to explain the unexplainable, to imagine a form of power so elegant it renders brute force obsolete. The theory suggests that if a stone's natural resonant frequency could be found and amplified, the material might become malleable or even defy gravity, gliding on a wave of sound. It is a poetic idea, one that transforms a construction site into a symphony of supernatural engineering. We must, however, hold these alluring tales against the light of physical evidence and reproducible experiment. Modern materials science shows that while sound waves can affect granular materials like sand, creating patterns and even allowing objects to appear to levitate in controlled demonstrations, the energy required to meaningfully soften or lift multi-ton solid granite blocks is of an entirely different magnitude. No experiment has ever demonstrated that sound, without modern electronic amplification on an industrial scale, could achieve the feats described in these legends. The practical methods we have explored, the ropes, the levers, the water levels, and the patient abrasion, all leave behind physical traces that archaeologists can find and validate, from quarry marks and tool grooves to the wear patterns on ancient hammerstones. These tangible clues form a coherent, evidence-based narrative of immense skill and logistics. So why do theories of acoustic mastery persist with such vigor? They emerge from the very real gaps in our understanding. While we can reconstruct the how of moving and fitting stones, The full experience of the building process, the precise social organization, the exact rituals, and the complete oral knowledge system remains partially lost to us. The theories fill those silent spaces with something that matches the scale of our awe. They remind us that the boundary between a fantastical myth and a genuinely lost, sophisticated technique can feel tantalizingly thin. What we dismiss as mere legend might sometimes preserve a fragmented memory of a principle we no longer fully grasp, perhaps not of literal levitation, but of using rhythm and coordinated sound to synchronize the efforts of hundreds of laborers, turning a chaotic hall into a unified, flowing motion. In the end, these speculative ideas serve a valuable purpose. They underscore that our rational explanations, though robust, may never completely capture the lived reality and the profound cultural spirit that raised these stones. The mystery, in its fullest sense, is not just a puzzle of physics, but an echo of human ambition that still resonates deeply within us. The most powerful answer to legend lies not in theory, but in action. To move beyond speculation, a dedicated group of researchers and craftsmen have taken up the tools of the past, embarking on a field known as experimental archaeology. Their mission is disarmingly simple: to test our historical deductions with physical labor, using only the materials and methods that would have been available thousands of years ago. The results are not just academic papers, they are sweat, blisters, and moments of profound revelation that bring the silent stones to life. At the Giza Plateau itself, experiments have shown that copper saws, long dismissed as too soft for hard stone, become effective cutting tools when paired with an abrasive slurry of quartz sand and water. As a team pulls the saw back and forth, the sand grains embed in the copper and do the actual cutting, slowly but surely grooving through granite. It is a noisy, laborious process, but it works, leaving tool marks that perfectly match those found on ancient blocks. Similarly, using a wooden drill with a copper tip and sand abrasive, experimenters have recreated the precise, conical holes found in unfinished obelisks and statues, proving that patience and the right technique could achieve what modern minds assumed required iron. In Peru, other teams have taken on the challenge of the megalithic transport. Using massive ropes woven from natural fibers, wooden sledges, and crews of volunteers, they have demonstrated how a multi-ton stone can be inched across the rugged landscape. The key, as suspected, is in the preparation of the path and the rhythm of the pull. By laying down a track of wooden sleepers and keeping it wet, friction is dramatically reduced. The real lesson, however, is in the human element. Coordinating dozens of people to pull in unison requires clear communication and leadership, often achieved through drumbeats or chants. These experiments reveal that the technology was as much social as it was mechanical, a symphony of coordinated effort that turned individual strength into a directed, monumental force. Perhaps the most humbling trials involve the final fitting of stones. Modern stonemasons attempting to replicate the polygonal walls of the Inca using only hammerstones and abrasives find that the process is incredibly slow, demanding an almost meditative level of focus. Yet, block by block, the method works. The soft fit technique, using clay to take an impression, proves to be a brilliantly effective way to custom carve a matching stone. These trials strip away the mystery of magic and replace it with something far more impressive, the tangible evidence of attainable human skill. These practical trials do more than prove feasibility, they fundamentally shift the narrative. Every successful experiment, every stone moved or shaped with period tools, chips away at the persistent myth of lost super science or extraterrestrial intervention. They redirect our awe to its proper place, onto the ingenuity, perseverance, and sheer collective will of ancient communities. Seeing a 20-ton block slide forward on a lubricated track, moved by the synchronized heave of 50 people, is a visceral experience. It translates abstract concepts of leverage and friction reduction into the straining muscles and coordinated shouts of real human beings. This perspective transforms these monuments from passive puzzles into active testaments. They become the frozen culmination of countless decisions, solved problems, and shared triumphs. The validation from experimental archaeology is compelling because it is not just logical, it is physical. It allows us to stand beside those ancient builders, not as bewildered admirers of the impossible, but as respectful peers who can finally appreciate the magnitude of their practical genius. The stones were not placed by a secret force, but by the applied intelligence of thousands of hands and minds, working in concert with the very laws of nature they had so carefully learned to observe. Yet the physical tools and celestial blueprints tell only half the story. A pyramid or a stone circle is not just a triumph of engineering, it is a monument to human organization. The greatest tool was not made of wood or stone, but of human society itself, a complex social engine capable of marshalling thousands of people toward a single, generational goal. To understand the alignment of stones, we must also understand the alignment of human hearts and minds. This required a social architecture as sophisticated as the physical one, built on administration, shared purpose, and an unwavering communal will. The form this took varied dramatically across cultures, revealing different paths to the same monumental end. In ancient Egypt, the effort was orchestrated by a powerful, centralized state. The pharaoh, considered a divine intermediary, provided not just the command, but the spiritual rationale. Vast administrative bureaucracies tracked everything from the daily bread rations for work crews to the output of distant quarries. Scribes kept meticulous records on papyrus, managing a rotating labor force that historical evidence suggests was not composed of slaves in the popular sense, but often of farmers working during the Nile's flood season, when their fields were underwater. They were fed, housed, and likely saw their labor as a religious duty, a service to the god-king that ensured cosmic order, or Maat, for the entire kingdom. This was a society channeling its collective surplus, both in grain and in human energy, into a project meant to secure eternity for its leader, and by extension for the nation itself. Contrast this with the rolling green hills of Neolithic Britain. At Stonehenge, there was no pharaoh, no central bureaucracy with written records. Here, the effort appears to have been a more communal, perhaps even a pilgrimage-based undertaking. Archaeologists believe the monument was built in stages over more than 1,000 years by different groups who shared a common cultural and spiritual vision. The transport and erection of the massive sarsen stones would have required the coordinated labor of many communities from across southern England, likely gathering at specific times of the year for seasonal festivals or ceremonial rites. The motivation was not to glorify a single ruler, but to create a shared sacred center, an axis mundi that connected multiple communities to the heavens and to each other. It was a project of unity where the act of building together may have been as important as the finished circle. In both models, the organization of labor was a breathtaking feat. Projects required not just brute strength, but a hierarchy of skill. There were master planners who understood astronomy and geometry, skilled quarrymen who could read the stone, experienced carpenters who built sledges and levers, and foremen who could translate shouts and drumbeats into synchronized action. Feeding, housing, and motivating this temporary city of workers was a logistical puzzle as complex as any geometric alignment. The shared cultural purpose was the glue that held it all together. Whether it was the Egyptian belief in a divine king's afterlife journey or the Neolithic understanding of a sacred landscape intertwined with celestial cycles, these projects were spiritual endeavors that provided meaning far beyond mere construction. They were acts of faith, symbols of identity, and declarations of a people's place in the cosmos. The stone they raised was a testament to what they collectively believed was worth a lifetime or many lifetimes of toil. When we look at the silent precision of these ancient sites, we are not just seeing aligned stones. We are witnessing the fossilized imprint of a society's highest aspirations, a snapshot of thousands of individuals pulling in the same direction, both literally and metaphorically. The true foundation of every megalith was this profound social contract, an agreement across generations that some goals are so magnificent, they are worth the patient labor of centuries. The stones themselves seem to whisper a hidden language of shape and proportion. While we have seen how ropes created perfect right angles and circles, a deeper layer of geometric intelligence is embedded within the walls and slopes of the most iconic structures. This moves us from practical alignment into the realm of mathematical discovery, where the very act of building may have revealed universal truths about number and form. Take the Great Pyramid of Giza. The ratio of its perimeter to its height is remarkably close to 2 times pi, the constant that defines the relationship between a circle's circumference and its diameter. For centuries, this has fueled intense debate. Did the Egyptian architects intentionally encode pi into the pyramid's dimensions as a symbolic gesture, linking the square base of the earth to the circle of the heavens? Or is this ratio an emergent property, a mathematical coincidence that arose naturally from their chosen slope angle and their simple, repetitive construction methods? Many scholars lean toward the latter, more elegant explanation. The builders likely established a desired steepness for the sides, a seeked in their terminology, which was a consistent ratio of vertical rise to horizontal run. When you build a pyramid with that specific, uniform slope, the relationship between its height and perimeter will automatically produce a figure very close to 2 pi. They were not thinking in abstract Greek symbols, but in the tangible reality of maintaining a constant angle across millions of blocks. In the process of solving that practical problem, they inadvertently brushed against a profound mathematical constant. A similar conversation surrounds the golden ratio, often represented by the Greek letter phi, approximately 1.618. This ratio appears in patterns throughout nature, from the spiral of a nautilus shell to the arrangement of leaves on a stem. Its aesthetic appeal has led many to search for it in ancient art and architecture, including the Parthenon in Athens. Analysis of the temple's facade shows that the relationship between its width and height and the spacing of its columns can be framed using rectangles that approximate the golden ratio. But was this a conscious design rule for the architects Ictinos and Callicrates? It is possible they used a geometric construction method that naturally yields this proportion. One simple way to approximate the golden ratio is with a straight edge and compass, tools they certainly possessed. By drawing a square, extending a line from its midpoint to an opposite corner, and using that length as a radius to define a new rectangle, you create a figure with golden ratio proportions. This was a geometric recipe, not an arithmetic calculation. The builders may have found this shape pleasing or symbolically resonant because it mirrored growth patterns they observed in the living world, and so they applied its geometry directly without ever naming the number phi. This distinction is crucial. It suggests that advanced mathematics was not a prerequisite for their engineering, but rather a consequence of it. Through generations of physically manipulating ropes to create circles, of setting out proportional rectangles to plan temple floors, and of refining slopes through trial and error, these cultures empirically discovered relationships that later mathematicians would define with equations. The knowledge was embedded in the craft itself, passed down as a set of practical rules of thumb, sacred geometries, and proven templates. A master mason did not need to solve for pi. He knew that if he used a wheel of a certain diameter to mark a foundation, the resulting circle would have a certain property. He discovered the truth through the material, not through the abstract. This mathematical mindset was therefore deeply intuitive and observational. It was born from a lifelong dialogue between the human hand and the physical world, a process of seeing patterns emerge from repetition and then choosing to codify those beautiful, stable patterns into stone. The perfection we admire is not a cryptic message left for us to decode, but the magnificent byproduct of a practical intelligence so attuned to its materials that it could not help but echo the fundamental geometry of the universe itself. The landscape was not merely a canvas to build upon, it was an active participant in the work. Beyond the grand constants of the sun and stars, ancient engineers possessed a deep ecological literacy, reading their immediate environment for 1,000 subtle cues that could guide a straight line or set a true angle. Their toolkit was not limited to what they could carry, it included the very properties of the world around them. Consider the challenge of establishing a perfectly straight line over a long distance, perhaps to lay out a processional avenue or a city's main thoroughfare. In a world before laser sights, one of the most reliable references was a river with a steady, placid flow. By observing the consistent current over a calm stretch, builders could use it as a living straightedge. They might float a series of markers downstream, adjusting their positions on the bank until each one traveled a perfectly parallel path, thus defining a line on land that mirrored the water's own direct course. This method turned a flowing resource into a dynamic surveyor's tool, its constancy providing a guide far straighter than any human eye could judge alone. Wind, too, became a design principle. In regions with strong, predictable prevailing winds, entire cities were often oriented to harness or mitigate their power. A settlement might be laid out so that its main streets channeled cooling summer breezes directly into its heart, while its thickest walls faced the direction of punishing winter storms. This was not just about comfort, it was a form of architectural alignment with a fundamental environmental force, using the wind's unwavering direction to dictate a city's geometry for reasons of resilience and livability. On a smaller, more tactile scale, the reflective surface of a still pond or a carefully filled basin of water offered another kind of precision. By sighting across the water, a builder could use the reflection of a distant marker or a pole to double-check alignments, essentially creating a simple optical level. If the reflection of a target point in the water aligned perfectly with the actual point when viewed from a specific position, it confirmed a level line of sight. This quiet, still surface became a mirror to truth, catching and confirming the builder's intentions. This profound partnership with nature extended even to the living world. There are compelling theories that certain cultures use the growth patterns of specific plants as seasonal markers. A tree that only bloomed when the sun reached a certain point in the sky could serve as a living calendar, its flowers signaling the ideal time to begin a foundation ceremony. The migratory paths of birds, always consistent, might have informed the axial alignment of a temple, linking it to a cycle of return and renewal. This deep, observant relationship meant that every element of the local ecology could potentially offer guidance. The builders were not imposing an abstract grid upon a passive land. They were listening to it, learning its rhythms, and then designing structures that resonated with those rhythms. This approach transformed construction from an act of dominion into one of collaboration. The straight line was not invented, it was discovered in the river's flow. The proper orientation was not decreed, it was learned from the wind's whisper. By making the earth itself a partner, these engineers achieved a precision that was not just technical, but deeply harmonious. Their greatest structures feel so rooted, so organically part of their settings, because in a very real sense, they grew from a conversation with the soil, the water, and the sky. Even the words they left behind are tools for our understanding. Language itself becomes a kind of archaeological site, where the specialized terms of the builder's craft are preserved like delicate artifacts. By examining these words, we can reconstruct not just how they worked, but how they thought, moving from the anonymous image of a laborer to the respected figure of a master craftsperson. In ancient Egypt, the term for an architect or master builder was Kari-Heb-Tep, which translates most directly to chief of the works. This is not a distant designer in an office, but a hands-on director, the one who knows every step from quarry to capstone. The title carries a sense of supreme responsibility and practical authority, someone who commanded both the celestial geometry and the gritty logistics of the work camp. It speaks to a culture that valued applied knowledge, where the highest professional honor was tied to the tangible act of creation. This linguistic clue reinforces the image we get from tomb paintings and tools of a stratified but integrated society where skilled professions held esteemed positions. Across the ocean, the Quechua language of the Inca holds its own technical lexicon. They had distinct words for different types of masonry and construction techniques. Perca referred to rough fieldstone walls built with mortar, practical for terraces and common buildings, but for the breathtaking, mortarless architecture of their temples and fortresses, they used the term Incalajta or similar descriptors implying fine masonry or imperial style. More tellingly, they had specific verbs and nouns for the act of fitting stones together. While the exact terms are debated by linguists, the existence of such specialized vocabulary is critical. It tells us that the process of shaping a polygonal block to its unique neighbor was not a vague, artistic endeavor. It was a recognized, nameable technique with its own steps and standards, taught from one generation of stonemasons to the next. The language formalizes the practice, turning intuitive skill into a transmissible craft. Analyzing these terms in the context of historical records and the structures themselves helps us reconstruct a lost mindset. When an Egyptian text mentions the stretching of the cord ceremony, performed by the pharaoh and a goddess to lay out a temple's foundation, the phrase is not merely poetic. It directly references the physical act of surveying with a knotted rope, elevating a practical engineering step into a sacred ritual. The technical and the spiritual were woven together in the very words they used. For the Inca, a word describing a perfectly fitted joint carried within it an entire philosophy of construction, one that valued seismic resilience, aesthetic harmony with the landscape, and the efficient use of naturally shaped stone. Their vocabulary reveals a pragmatic intelligence that solved problems with the materials at hand, celebrating the solution in their language. This linguistic investigation does profound work. It moves us from seeing these wonders as the products of a faceless, monolithic ancient society to recognizing the individuals within it, the chief of the works and his teams of specialized masons. These were professionals who spent lifetimes honing their senses, who could judge a true surface by the ring of a hammerstone or the shadow along a cord. They had names for their tools, their techniques, and their errors. They were not anonymous laborers, but craftspeople whose knowledge was so vital it shaped the very words of their culture. By recovering these terms, we demystify the process one step further. It was not a supernatural event, but a human craft, elevated to its highest possible expression through patience, observation, and a technical vocabulary passed down through generations. The stones are silent, but the words that built them still echo, telling us that the greatest precision often begins with simply knowing what to call what you are doing. Our instinct is to measure their achievements against our own technological yardstick, and in doing so, we often create a distorted picture of the past. One of the most persistent modern projections is the idea of a primitive society, a term that carries a heavy, unspoken judgment of inferiority. To call a culture that charted the stars with naked eye precision, that engineered seismic resilience into stone, and that organized multi-generational projects primitive is to fundamentally misunderstand the nature of intelligence. Their brilliance was not oriented toward the rapid, machine-driven production we value today, but toward a deep, patient partnership with their environment. They possessed a different kind of sophistication, one built on cumulative observation, material intimacy, and a timescale of legacy that stretches beyond a single human life. This mislabeling often walks hand in hand with another powerful myth, the image of endless slave labor driven by the crack of a whip. While popular culture has painted vivid scenes of suffering masses toiling under tyranny, the archaeological and historical evidence points in a more nuanced direction. In ancient Egypt, for instance, records from worker villages near the Giza Plateau show communities of skilled laborers, artisans, and their families who were provided with housing, medical care, and regular rations of bread and beer. Many were likely farmers who worked on state projects during the annual inundation of the Nile, when their fields were underwater. This was a form of organized seasonal civic service, a duty to the divine king and the cosmic order, not the chattel slavery of later eras. Similarly, the communal monuments of Neolithic Europe or the Andes suggest projects woven into the social and ceremonial fabric of society, where contributing labor was part of one's identity and spiritual practice. To reduce these profound communal efforts to mere coercion is to strip them of their cultural meaning and to underestimate the powerful human drive to collectively create something magnificent. A third common error is to look at a slightly leaning wall or a gap that has appeared between stones and assume the builder's precision has been overstated by enthusiasts. What this view misses is the relentless work of time. These structures have endured for thousands of years, sitting upon shifting soils, surviving earthquakes, and weathering countless freeze-thaw cycles. The natural settlement of foundations over millennia, the minute movements of continents, and the slow erosion by wind and rain all introduce changes the original engineers could never have prevented. The miracle is not that a joint has opened by a few millimeters after 4,000 years, but that the joint exists at all, that the core alignment remains so breathtakingly true. When we see the corner of the Great Pyramid still pointing almost perfectly north, or an Inca wall still standing without mortar after seismic events that flatten modern cities, we are not seeing overstated precision. We are witnessing precision that was so fundamentally sound it could absorb the chaos of ages and still declare its original intent. Correcting these misconceptions is not just an academic exercise. It reshapes how we see human potential. It asks us to value a different set of skills, the kind that comes from watching the same horizon for a lifetime, from learning the grain of a granite face by touch, and from trusting that a project you start will be finished by your grandchildren. Their intelligence was not lesser for lacking steel or silicon. It was profoundly adapted to its context, achieving feats that our own technology, for all its power, might struggle to replicate under the same constraints. The true measure of their genius is not that they built without modern tools, but that they built so perfectly with the tools they had, turning simple observation and collective will into monuments that continue to teach us about time, resilience, and the enduring desire to reach for the sky. The stones themselves hold the most honest record of their creation, etched not in ink but in granite and limestone. To walk through an ancient quarry or run a hand along a temple wall is to read a diary of physical effort, written in a language of scars and grooves. These tool marks are the fingerprints of the builders, a direct and undeniable witness to their methods. In the quarries of Aswan, Egypt, the unyielding granite face is pocked with thousands of small, circular depressions. These are the unmistakable signatures of stone mauls, hammerstones of dolerite swung in relentless rhythm by teams of workers. Each pockmark represents a calculated blow, not random violence, but a systematic effort to fracture the bedrock along a predetermined line. The pattern of these marks tells a clear story of patience and controlled force, a technique of pounding a groove until the stone surrendered along a clean plane. Half a world away, on a mountainside in Peru, the evidence speaks in a different dialect. Here, on partially worked blocks at sites like Ollantaytambo, you can find long, parallel grooves scored into the andesite. These are not the marks of pounding but of sawing. Researchers believe these grooves were made by pulling a rope or a leather strap back and forth, using an abrasive slurry of sand and water. The gritty paste did the actual cutting, while the cord simply provided the motion, wearing down the stone grain by grain over days or weeks. The parallel lines show a steady, sustained action, a different kind of patience that favored persistent abrasion over percussive force. Equally telling are the strategic holes drilled or pounded into stone, the anchor points for levers and wedges. In many quarries, you can find a line of such holes along the base of a block, where wooden wedges were inserted and then soaked with water. As the wood swelled, it generated immense, even pressure, cleanly prying the monolith from its cradle. These holes are like surgical incisions, precise interventions that allowed human ingenuity to overcome impossible weight through understanding, not brute strength. Perhaps even more valuable than the perfect walls, however, are the mistakes. An abandoned obelisk cracked and left in its quarry bed at Aswan is a frozen moment of problem solving. It shows where the calculations of stress failed, where the stone's hidden flaw betrayed the workers' efforts. This failure is a priceless lesson, revealing the limits of their knowledge and the risks they took. Similarly, a slightly misaligned course of stones in a temple wall, later corrected in the next layer, speaks volumes. It shows that the process was not infallible magic, but a series of checks and adjustments. The builders had to constantly verify their work, and sometimes they had to adapt. These scars and errors transform the silent monuments into a chorus of human experience. They tell a story of trial and relentless error correction, of a problem identified and a new technique attempted. Each pockmark, each groove, each abandoned block is a testament to the learning process, to the countless small decisions made under the sun. They remind us that the perfect product we admire today is the final draft of a story written in dust and effort, where every correction brought them closer to an ideal that would outlast them all. The tools left behind in the dust tell a story of adaptation. When we place the methods of the Egyptian pyramid builders side by side with those of the Inca stonemasons, a compelling truth emerges. Different environments and materials forge distinct paths to the same breathtaking end. Both cultures faced the monumental challenge of aligning and fitting stone with impossible precision, yet the solutions they crafted were a direct reflection of the world they inhabited. In the sun-baked valleys of Egypt, the primary building materials were limestone and the occasional granite, stones that, while hard, could be worked with persistent abrasion. The Egyptian toolkit thus featured copper, a relatively soft metal that became powerful when paired with a simple abrasive like quartz sand. Saws and drills made of copper, pulled back and forth by teams of workers, used the grinding power of the sand to slowly, methodically cut through stone. It was a process that traded metal's hardness for the relentless, granular action of a substance as common as the desert itself. Their precision came from this marriage of a malleable metal and an abundant natural abrasive, allowing them to shape blocks and create the smooth, planar surfaces needed for their geometric monuments. High in the Andes, the Inca confronted a different geological reality. Their world was built upon andesite, a volcanic stone of formidable hardness that would have quickly dulled copper tools. Their response was to eliminate metal from the equation almost entirely. The Inca method was one of direct stone-on-stone conversation. They used hammerstones of even harder rock, like black basalt, to pound and peck at the andesite, fracturing it with controlled percussion. For the final, seamless fitting of their legendary polygonal walls, they relied on the patient grinding of stone against stone with sand slurry, a technique that required immense time but yielded joints that locked together by friction alone. Their precision emerged not from cutting but from a persistent reduction, a gradual wearing away of high points until two unique faces became mirror images. This fundamental difference in approach speaks to a profound environmental intelligence. The Egyptians, with access to copper mines and vast deserts of sand, developed a technology that leveraged those specific resources. The Incas, surrounded by mountains of tough volcanic rock, mastered the art of persuading stone with stone itself. Despite these divergent tools, the outcomes achieved a hauntingly similar grandeur. The perfectly fitted casing stones of the Great Pyramid and the interlocking puzzle of an Inca fortress wall both achieve a result that defies simple explanation. This convergence is where we see the universal human capacity for creative problem solving under extreme constraints. It proves there was no single lost secret passed between these separated continents. Instead, it reveals that when faced with the same core challenge, to make stone obey human will and celestial alignment, intelligent minds arrived at elegant, locally sourced solutions. The Egyptian leaning into abrasion and the Inca mastering percussion were both brilliant adaptations, proving that the path to precision is not a straight line dictated by a specific technology. It is a winding road shaped by the materials at hand, the landscape underfoot, and the relentless creativity of communities determined to build legacies in stone. The wonder is not that they used different methods, but that those different methods led them to the same awe-inspiring destination, a testament to the adaptable and ingenious spirit of humanity itself. The line between the engineer's calculation and the priest's prayer was often invisible. When a master builder sighted the rising sun to set his foundation, he was not just solving a geometric problem, he was performing a sacred act. For these cultures, the universe was an ordered, living system, and to build in perfect alignment with it was to participate in that divine order, to make their creation a true microcosm of the cosmos. This spiritual imperative transformed every practical step into a ritual, weaving a layer of symbolic meaning that may have been the ultimate guarantor of their precision. The process likely began with a ceremony of consecration, a formal asking of permission from the spirits of the land or the gods of the earth. Before a single surveyor's cord was stretched, priests and elders would walk the proposed site, making offerings and interpreting signs. This was not superstition, but a profound acknowledgement that they were about to alter a sacred landscape. By ritually cleansing and dedicating the ground, they established a psychological and social boundary, marking the space as special, set apart for a work of eternal significance. This ceremony elevated the project in the minds of every participant, from the chief architect to the newest laborer. It framed the coming years of backbreaking toil not as mere construction, but as a collective spiritual journey, a service to the gods that demanded their utmost care. The most famous example of this fusion is the Egyptian stretching of the cord ritual. Depicted in temple reliefs, it shows the pharaoh, assisted by the goddess Sekhet, hammering stakes into the ground and pulling a cord taut to lay out a temple's foundation. This was not a metaphorical scene. It was the literal, ceremonial enactment of the very surveying technique they used. By involving the divine in the practical act, they imbued the resulting straight line with cosmic authority. To deviate from that line in construction would not just be a technical error, it would be a religious transgression, a rupture in the sacred order they were striving to embody. This symbolic weight enforced a discipline that a simple foreman's command could never match. The drive for perfect alignment became a devotional act. Consider the solstice alignment of a temple. Achieving this required observing the sun's slow crawl along the horizon for years, marking its extreme turning points with unwavering patience. This long-term observation was itself a form of ritual, a calendar kept by the community. When the great day arrived and the dawn sun finally streamed down the temple's central axis to illuminate the inner sanctum, it was the dramatic climax of that ritual. The light was not just illuminating a dark chamber, It was proving the temple's holiness, demonstrating that the builders had successfully captured a moment of celestial power in stone. That annual event would renew the community's faith and justify the immense effort, turning the architecture into a perpetual machine for generating awe and reinforcing cosmic connection. This symbolic layer provided something pure utility could not, a transcendent motivation that spanned generations, a project meant to last for eternity, to serve as a bridge between the human and the divine, could not tolerate shoddy workmanship. The belief that the gods themselves would inhabit this structure, or that a pharaoh's soul would ascend to the stars along its precise angles, demanded perfection. It fostered a culture of craftsmanship where the mason's pride was intertwined with piety. To shape a stone perfectly was to honor the gods, to ensure the cosmic machinery would function. This mindset cultivated an attention to detail, a willingness to spend months on a single joint that went far beyond what was structurally necessary. The quest for cosmological harmony did not distract from practical precision. It was the very engine that powered it. In the end, the silent, perfect stones we admire today are not just feats of engineering. They are the physical remnants of a profound conversation between humanity and the universe, where every aligned corner was a word in a prayer built to last forever. This legacy mindset is etched into the very physics of their walls. A perfectly fitted dry stone joint is not merely a display of skill, it is a profound act of foresight. In regions like the Andes, where the earth shudders, the interlocking puzzle of a polygonal wall transforms seismic energy from a destructive force into a dynamic conversation. During a tremor, the stones in a rigid, mortared wall would try to move as one solid unit, creating catastrophic stress points that lead to collapse. But in a dry stone wall, the irregular shapes allow for minute, individual movements. The stones shift and settle against one another, absorbing and dissipating the energy before settling back into a stable configuration. The builders did not just align stones for the present, they aligned them for a future they knew would include violent upheavals, designing resilience directly into the geometry. The structure was not meant to simply stand, it was meant to endure the unpredictable wrath of the planet itself. Their astronomical alignments served a similar long-term purpose, transforming architecture into a perpetual cultural engine. A temple doorway that captures the solstice sunrise is not a static feature. It is a machine that operates once a year for millennia. Long after the names of the kings and priests were forgotten, the sun would continue its silent performance, streaming down the prescribed axis on the appointed day. This ensured the site retained its power and meaning. It could be rediscovered by later peoples, its function as a calendar still legible, its connection to the cosmos still palpable. The alignment guaranteed the structure would not become a meaningless ruin, but would remain a participant in the ongoing story of the sky, offering its silent testimony to every generation that followed. It was a way of hard-coding cultural relevance into stone, making the building a teacher for ages it would never see. This philosophy extended to the most fundamental choices, like the selection of materials. They did not use the most convenient stone, they used the most durable. Granite, basalt, andesite, these are some of the hardest substances on Earth, incredibly difficult to work but nearly impervious to time. The effort invested in quarrying and shaping them was a direct investment in longevity. Furthermore, they consistently over-engineered. The Great Pyramid's core masonry is vastly more robust than required to support its own weight. The lintels at Stonehenge are secured with complex mortise and tenon joints, a woodworking technique rendered in immovable stone, providing stability far beyond a simple stacked design. This was not inefficiency, it was insurance. They built with a margin of safety meant to span centuries of weathering, settling, and unforeseen events. They were not constructing for a client's lifetime or even a dynasty's, but for a timeline that blurred into legend. In the end, this is the most humbling lesson whispered by these aligned stones. The ancient engineers, by fixing their sights on the unchanging stars and the slow turn of the seasons, were also fixing a gaze upon a distant future. Their precision was a form of communication. In the seamless joint, they said, we understood the earth. In the solstice alignment, they said, we understood the sky. And in the choice to undertake a project that would outlive everyone involved by generations, they said, we trust you, our descendants, to find meaning in this. They aligned their work with eternity, and in doing so, they sent a message in the most durable medium they could conceive, a message that has reached us not as a whisper, but as a shout across the ages. The true alignment was not just north to south, but past to future, a bridge of stone built with the quiet confidence that someone, someday, would stand before it and understand. Yet the stones ask us a final, pressing question. What can our world of instant data and disposable materials possibly learn from these patient masters of granite and sunlight? The answer is written not in their forgotten languages, but in the principles their work embodies, principles that feel urgently modern. Consider their profound commitment to local materials. They did not import granite from across oceans at great energy cost. They used the stone beneath their feet, the clay from their riverbanks, the timber from their forests. This was not a limitation, but a source of genius, forcing an intimate understanding of the material's strengths and personality. Today, we call this bioregional design, and it is a cornerstone of sustainable architecture. Their structures are the ultimate examples of passive solar alignment, oriented to capture warmth in winter and coolness in summer without a single watt of electricity. A temple aligned to the winter solstice sun pulls in low, warming rays precisely when heat is most needed, a lesson our glass skyscrapers, which often require massive heating and cooling systems to counteract poor design, have only recently begun to relearn. Their engineering was a dialogue with the climate, not a battle against it, offering a blueprint for resilience in an era of changing planetary systems. Their social model holds another profound lesson. These were not projects built by anonymous corporations, but by communities united around a shared, transcendent purpose. The organization required to feed, house, and coordinate thousands of people toward a generational goal represents a masterpiece of human collaboration. In our world of fragmented attention and short-term projects, their ability to maintain focus and quality across decades, even centuries, is staggering. It speaks to the power of a unifying vision, one that gave meaning to every individual's labor. Modern project managers and open-source software communities, which coordinate global contributors around a common digital build, are rediscovering this ancient truth that the most complex systems are best built by engaged communities, not just top-down commands. The pyramid or stone circle was the original crowd-sourced project, proving that collective intelligence, properly channeled, can achieve the impossible. Perhaps their most vital gift to us is a mindset, a way of seeing. In an age of rapid, disposable technology, they championed the values of deep observation and patient iteration. They spent lifetimes watching the sky before marking a single line on the ground. They were willing to spend months grinding two stones together for a perfect fit, understanding that time itself was a tool for achieving permanence. We live in a culture that often prioritizes speed over durability, quick fixes over lasting solutions. Their work stands as a silent rebuke to this haste, a monument to the idea that some things are worth doing slowly and doing right. They worked in harmony with natural forces, using gravity with the Plumb bob, water's level with the foundation trench, and thermal stress in the quarry. They saw themselves as partners within a living system, not as its conquerors. This philosophy of cooperation with nature, rather than domination, is perhaps the most critical lesson we could take from them as we face global environmental challenges. They remind us that true precision is not about control, but about understanding, alignment, and respect. Their stones do not just point to the North Star, they point toward a more thoughtful, resilient, and purposeful way of building our world, one careful observation at a time. From the celestial maps of Egypt to the seismic jigsaw puzzles of the Andes, we have journeyed through the brilliant minds of ancient engineers. They aligned massive stones not with magic, but with a profound mastery of the world around them, using water as a level, the stars as a compass, and simple geometry as their calculator. These monuments are testaments to human ingenuity, patience, and our enduring desire to connect our creations to the cosmos. The next time you see an image of a pyramid or an Inca wall, you will see the ghost of a plumb line, the echo of a star's transit, and the indelible mark of human hands achieving the impossible. If this exploration of lost knowledge captivated you, subscribe for more journeys into history's greatest mysteries, and share your thoughts on these ancient techniques in the comments below.